Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to talk about entropy and the second law of thermodynamics. So in my last video we were talking about the need for some sort of chemical potential in order to explain the spontaneity of chemical reactions. So we were talking about mechanical systems like dropping a book or rolling a ball down a hill or a slope or something like that, and how those are spontaneous because there's a gravitational field, and we can talk about gravitational potential energy and how those mechanical objects tend to want to lower their gravitational potential energy. And so maybe there's something like a chemical potential that can explain the spontaneity of reactions. So one of the first things to come to mind is enthalpy. What about enthalpy? Maybe there are chemical systems that need to proceed in a direction towards lowest enthalpy. So maybe that's the goal, is going towards the lower enthalpy is what drives the spontaneity of the reaction. And so to remind ourselves what we mean by enthalpy is that it is the sum of what is known as the internal energy plus the product of the pressure times the volume, right? So these two things added together is your enthalpy. And remember, enthalpy is referred to or symbolized by H, or the change in enthalpy for a reaction would be your delta H. And so maybe the drive towards lower enthalpy is what's driving the spontaneity of the reactions. So if this is true, however, then all exothermic reactions or processes would be spontaneous, and all endothermic ones would not be spontaneous. So just to remind ourselves, exothermic reactions or processes are ones in which energy is given off so that the system itself is releasing energy into the surroundings, and so the system is losing energy. And so that would be exothermic. Exo meaning out of, therm referring to heat, right? So exothermic would be those that are systems or processes or reactions that are releasing heat to the surroundings. Endothermic would be those that are absorbing heat or energy from the surroundings. So if the goal is to have less energy, then the exothermic ones would be spontaneous, and the endothermics would not be spontaneous. However, although most spontaneous processes are exothermic, not all of them are. And so here's a few examples. So the melting of ice above 0 degrees, that's a spontaneous reaction, but in order to get that to go, it's absorbing heat from the surroundings in order to cause the ice to melt. Evaporation of liquid water into gaseous water. Again, spontaneous, right? You spill water on the table or you pour water out on a surface. After a while, it disappears, it evaporates. You don't need to do anything more to it. But that again requires the absorption of energy from the surroundings. So there, the water is gaining energy, and also the dissolution of sodium chloride in water. So you put it in water and it spontaneously uh, uh, dissolves, right? And again, that's going to be one where it's absorbing energy instead of releasing energy. So, so we need to understand these processes and see, okay, what do these processes have in common that might explain why they go in this direction? And that's where we see that all of them become more disordered, right? So when you melt ice, right, what's happening to the water molecules? The water molecules, when it's a solid ice form, solid form, those water molecules are stuck in place. They're in an ordered, like hexagonal structure with the hydrogen bonds. And so it's very ordered. The molecules are not moving around. So there you have order. And then when you melt the ice, what's happening to the water molecules? Water molecules are moving faster as they gain more energy from the heat of the surroundings. and then they start to move from place to place and move around each other. And so it becomes more disordered, right? So more randomness in the system. Same thing with evaporation. So you're taking liquid water, and the liquid water is again absorbing heat from the surroundings. The water molecules are moving even faster to the point where they can move away from each other and indefinitely move away from each other in the form of gas. And there you have even more randomness, more disorder in the system, right? As you go from liquid water molecules that are kind of close together still but moving around to where they can move apart, far apart from each other, and occupy different spaces. And finally, dissolution of sodium chloride, same thing here. You start with a solid crystal of ordered sodium ions and chloride ions in a crystal. You put that in the water and they dissolve, they spread out, they separate from each other. And so you don't have that nice ordered structure anymore. And so now you have more disorder as they move away, and then they can occupy different places in the solution, and they can move around from each other very far from each other, like a sort of like a gas. So all three of these have in common that you move from an ordered system to a more disordered system. And so this order or disorder here is what we refer to as entropy. So entropy is increases for all three of these. So, but what is entropy exactly? So entropy, informally, we understand that as disorder or randomness. But this is only an analogy to what's really going on for chemical systems. But it is helpful to understand. So the analogy is a good thing, but that's what we could talk about informally. But formally, when we define entropy, it's defined as, and we use the symbol S. So the symbol S for entropy, it is a thermodynamic function that increases. So it's a function that increases. So we're talking about entropy. Entropy is a function, a thermodynamic function that increases what? Increases with the number of energetically equivalent ways or states to arrange the components of a system to achieve a particular state. So then here, what do we mean by energetically equivalent ways? So that's important to understand, and we'll talk about that in just a moment. But one thing you want to keep in mind is what does it mean by energetically equivalent ways? So if I have, say, I have one marker, this green marker here, and maybe there's one way to put this marker because there's only one marker here. So I can't arrange this marker in any way. It's just this one marker, right? So this is just one energetically possible state that it could be in. But what if I have another marker? So if I add a blue marker here, right? So I'll put my black marker down here. So now we have a blue and green marker. So maybe that's one possible energetic state, right? But what if I switch them this way? Now they're switched. So that's a second equivalent energetic state, right? So they're both occupying similar positions to each other, but instead of being right and left, they switch places. So maybe that would be two possible equivalent states, right? So this has more possible equivalent states than just having the one marker. What if I throw a third marker in here? So the third marker, if I can hold these well, so I have black, green, and blue. So now with the equivalent states here, right, so this could be one possible equivalent state, but maybe if I switch the blue marker with the green, right, so now the blue's in the middle, so that would be a second equivalent state, or maybe I put the blue on the other side of the black marker, so that would be a third one, right? Or maybe I put the black marker there. That would be a fourth one. So you could see that there are different ways of arranging these markers so that they are in a different position. And that might be analogous to having different states or different ways, energetically equivalent ways to arrange your system, right? So this is kind of an analogous way of seeing or understanding what do we mean by the number of energetically equivalent ways to arrange the components of a system. So the more ways you can arrange these particles or the components of a system that are energetically equivalent to each other, then that would be more entropy. So the more markers I have, the more ways I can arrange them, and therefore the higher entropy. So here I have 2 markers, so therefore there's more ways to arrange these 2 markers than it is to raise 1, so the entropy could be greater for this, and so on. So for the third, and if I kept adding more markers, then the number of equivalent ways that I could arrange those markers so that they were equivalent would be greater. So that would be increasing entropy. So so right now I will go ahead and I'll talk about the what it means to be entropy a little bit, and I'll tie that to macro states and micro states. So give me 1 second while I rearrange the board. I did forget about one thing though. So here, when we're talking about increasing in entropy, here we have an equation. So it's called the entropy equation here. Here we have our symbol for entropy. Entropy is equal to K. K is known as the Boltzmann constant, and the Boltzmann constant is the gas constant R. So yes, that's the ideal gas law constant R divided by the Avogadro's number, Na. So Avogadro's number, and that gives us 1.38 times 10 to the negative 3 joules per Kelvin. So it's the Boltzmann constant multiplied by the natural log of W. And W is the number of energetically equivalent ways to arrange the components of a system. So what are those energetically equivalent ways of arrangement? I'm going to talk about that in just a moment, so hang on for just 1 second. Okay, so let's talk about microstates and macrostates. So here's the equation again. So we have the entropy S is equal to the Boltzmann constant multiplied by the natural log of W. And as I said before, W is the number of energetically equivalent ways to arrange the components of a system. So I want to talk a little bit about that and try to explain what that means using an example. So if we take a system of particles, so let's imagine we have a system of particles, has a certain number of particles in it. This could be something like a fixed amount of an ideal gas, right? So we have an ideal gas in a container, right? There's a certain number of particles in there, and we can kind of imagine that sort of situation. And so when we're talking about the macro state, what we mean there is a given set of conditions for that state on the macroscopic scale. So this would be like for our ideal gas, this would be pressure, volume, and the temperature of the gas. So as long as these conditions, pressure, volume, and temperature of the gas remain constant, the energy of the system remains constant, right? So we're thinking of it on the macroscopic scale here, right? So we have this gas, we have it at a constant pressure, volume, and temperature, then the energy of that gas is going to remain constant as long as those remain constant. However, where that energy is in the gas is not constant. So at any instant, the energy of the particles change, right? So this is because the particles are moving around, they're colliding with each other. So that way one particle may have a high energy at one moment, but through collisions, it might lose that energy and then be slower at any other instant of time. So it have less energy. So where that energy ends up in the system is always constantly changing because the particles are moving, the particles are constantly colliding with each other and transferring energy from one particle to the next. So although at the macro scale with the macro state, the pressure, volume, and temperature are constant, and therefore the energy of the gas is constant, where that energy is not constant. And so that brings us to the micro state. So the micro state is the exact internal energy distribution, right? How that energy is distributed among the particles at any one instant. So as I said, because the particles are always moving around, they're colliding with each other, at any one instant, any particle can have less or more energy depending on its collisions and how it got that energy or giving off energy to other particles through collisions. And so again, here would be kind of a very simplified version of this gas, right? So if I have two systems of particles, so if we think of W, we think of W in terms of microstates, right? So when we're thinking about energetically equivalent waves, think of that as microstates. So here we have system A, and system A only has one energy level, the energy level at 2 joules of energy. And system B has two energy levels. We have one at 3 joules of energy and one at 1 joule of energy. And so in system A, both the red and blue particles are at the same energy level. And so each of them have 2 joules of energy. So for a total of 4 joules of energy in system A. So here's our gas, for example, right? And so here's another system B that has 2 energy levels. So one particle can occupy the bottom one, and one particle can occupy the higher one. So then we have one at 1 joule, one at 3 joules. You add that together, you get 4 joules. So this system here, the total energy of this system is identical to the total energy of this system. So we have 4 joules total here, we have 4 joules total here, but you'll notice that the particles here can switch places and you can get a different microstate. So here's one microstate, and then here's another microstate of system B. So here, instead of the blue particle being on the bottom 1 joule and the red being on top with 3 joules, you can see that the red could be on the bottom with 1 joule and the blue on top with 3 joules. So same energy. So this is this microstate of system B has the same energy of this microstate, 4 joules, but because they have different positions, it's a different microstate. So here we can see that system B has the same energy as system A, but you can see here that there's only one microstate possible for system A, whereas for system B, there's 2 microstates, equivalent energy, microstates that have equivalent energy. There's 2 possible microstates. And so here, because you have more equivalent microstates here, right? Again, number of equivalent, energetically equivalent ways to arrange the components of the system, we can understand it as a microstate. And so here, since system B has more microstates, more equivalent ways to arrange the components, energetically equivalent ways, then this means that system B has a higher entropy than system A. And so we can think about this in terms of energy. So if we take a sidestep and talk about energy, we'll talk about that next. and we'll continue the discussion in just a second. Okay, so let's turn our attention to energy just for a moment. So we're talking about microstates and macrostates. And so here again is our equation, and that W, so the entropy is equal to the Boltzmann constant multiplied by the natural log of W, and W is again the number of energetically equivalent ways to arrange the components of a system. And so if we're thinking about the energy for a moment, we think of entropy, the entropy of a state, if we look here, the entropy S of a state increases with the number of energetically equivalent ways to arrange the components of the system, right? So to energetically equivalent is key here. So we want energetically equivalent ways to arrange the components of a system in order to achieve that particular state. And so what this implies here is that the energy, or the state, with the highest entropy also has the greatest dispersal of energy, right? So we want more energetically equivalent ways to arrange those components. So if we can disperse that energy in more than less, then that seems to indicate that entropy is tied to the greatest dispersal of energy. And we saw that in the example earlier with the two state systems. We had system A, which there was only one energy level for the two particles to occupy. And so there wasn't much of a dispersal of the energy into different energy levels, right? So when you had system B that had two energy levels, right, you could disperse that energy more, and then you could get more equivalent ways to arrange the components of the system, right? You could have the blue particle on the bottom and the red on top, or you could have the blue on top and the red on the bottom. So those are two equivalent ways. So you had more ways to disperse the energy of the system, the particles, and keeping the total energy of the system the same, right? So there seems to be that correlation. So again, the state that has the highest entropy seems to also have the greatest dispersal of energy, and therefore a state in which a given amount of energy is more highly dispersed or more highly randomized has more entropy than a state in which the same energy is more highly concentrated. So we're now tying this idea of randomized energy, right? More highly randomized, where the energy is more dispersed rather than concentrated. And so if we can tie this entropy to the dispersal or randomization of energy, then we can state the second law of thermodynamics in terms of the dispersal of energy. And so here, the second law of thermodynamics then is, for any spontaneous process, the energy of the universe the entropy of the universe is increased. So delta S of the universe is greater than 0. So we found a way of understanding the increase, or understand spontaneity of reactions. So spontaneity of reactions or chemical systems is tied to this idea of microstates, this having the energetically equivalent ways to arrange the components of the system, tied to the also greater dispersal of energy. So we can now understand that spontaneous systems or spontaneous processes are going to be ones that increase the entropy of the universe, And so how does the entropy of the universe increase? That means that the energy of the universe is more dispersed. It's more randomized in the universe. So any process then, so if you understand this, any process or reaction, any chemical process or reaction that increases the entropy of the universe is going to be one that is going to be spontaneous. Any reaction that decreases the amount of entropy in the universe is going to be one that is non-spontaneous. And so that is going to be a measure of so the measurement of entropy, or how entropy changes for the universe, is going to be a measure or indicator of whether this is going to be a spontaneous or non-spontaneous process. And so one other thing to keep in mind is that entropy is a state function like enthalpy. So what does that mean? Again, a state function is a function that does not depend on how you got from A to B. It just depends on what the state is at A and what the state is at B. So it's your initial state and your final state that really is what the function is dependent upon. It doesn't matter how you got from A and B. So for example, you can think of this in terms of either, if I'm standing on the ground floor of a hotel or a building and I want to go to the top floor, I have a couple of ways to get there. I could either take the elevator or walk up the stairs. So if we're thinking of this as a state function, it doesn't matter how I got to the top floor. As far as my energy goes, if we're thinking about my gravitational potential energy, all it matters is that I start at ground level and I go up to the top floor, and my change in energy between the bottom floor and the top floor is all that matters. It doesn't matter how I got to that top floor. So that is what we mean by a state function. So since entropy is a state function like enthalpy, then the change in entropy is just going to be whatever the final entropy is minus the initial entropy. That's all that you need. And so I'm now going to go ahead and compare this or use another example of how this can be applied to the ideal gas that we were talking about before. So give me 1 second. Okay, welcome back. And so in this segment of the video, I'm going to talk about how we can apply what we've just talked about to the expansion of an ideal gas. So what we have here is, let's say we have a flask here that contains an ideal gas, and it's connected to a vacuum, a flask that is evacuated. There's no particles in this flask. And let's remind ourselves that work is equal to the negative of the external pressure times the change in volume. So if we remember that the total energy of the system, the enthalpy, so I said enthalpy is equal to the internal energy plus the pressure times the volume. The pressure times the volume is the work, so enthalpy is equal to Q plus W. Since we have a vacuum here, there is no external pressure against which the ideal gas would have to expand into when you open the stopcock here. So here, the two flasks are separated from each other, but we're wondering what's going to happen when we open this stopcock, we open the valve here and let the gas be able to expand. Well, there's not going to be an external pressure because it's a vacuum, so we don't need to worry about work as a change in energy. And so the only thing we need to worry about is the internal energy of the particles. And here we're assuming that that's constant because it's an ideal gas. They're not really attracted to each other. The particles don't influence each other. The particles will have the same energy in this flask as they do in this flask. So energy is going to be constant. So